Electrical power produced in the world is transmitted by the use of alternating current. AC current is used in the home for operating television sets, computers, and other home appliances. And it's also found in all of our largest industries, powering things like large motors and electric furnaces. An electrical current is described as the movement of free electrons from atom to atom in a conductor. The current flows as long as there is a difference of potential present. If the polarity of this potential difference or voltage never changes, the current always flows in one direction and is called direct current. There is a type of electric current that does not always flow in the same direction. The current alternates, flowing first in one direction, then reversing and flowing in the opposite direction. This type of current is called alternating current or AC. The schematic symbol for an AC power source is a sine wave inside a circle. In the case of DC current, the electrons flow in one direction only, and the current is measured by counting the number of electrons flowing past a point in a circuit. If 1 coulomb of electrons moves past a point in a circuit in 1 second with all the electrons moving in the same direction, the current flow is 1 ampere DC. If 1/2 coulomb of electrons moves past a point in the circuit in 1/2 second, then reverses direction and moves past the same point in the opposite direction during the next 1/2 second, then a total of 1 coulomb of electrons passes the same point in 1 second, the current flow is 1 ampere AC. Since the current reverses direction, it may seem that anything it would do while flowing in one direction, it would undo when it's flowing in the opposite direction. Remember, it's not the flow of electrons that do any useful work, but the effect they have on the loads they flow through. For example, a soldering iron will heat when supplied with either direct current or alternating current. Basically, alternating current can do everything that direct current can and more. AC voltage can be increased or decreased easily through the use of transformers. Low-voltage power produced by generators can be increased through the use of large step-up transformers to be delivered over electrical transmission lines from city to city. At a substation, this high voltage is decreased to a lower voltage for distribution within a city, town, or suburb. And finally, a power line step-down transformer reduces the voltage, so it may be used in homes and industry. Alternating current has other characteristics that make it useful. It varies in a similar manner as do sound waves in the air. Therefore, alternating current is used in the field of electrical communications to reproduce and transmit sound electrically. Another important characteristic of alternating current is the fact that electrical energy radiates from a circuit in which AC is flowing. This principle is the basis of radio communications and is used in the field of radio and television. Mechanical generators produce alternating current. They are known as AC generators or alternators. To understand alternating current, it will be necessary to visualize how a voltage or current changes over a period of time. A graphical representation showing the magnitude and direction of a voltage or current at every instant of time is called a waveform. 2 axes must first be laid out. The vertical axis represents the value and the polarity of the voltage. The horizontal axis is used as the time base. It is divided into degrees of rotation or suitable divisions of time. To help you understand how AC voltage is produced and the waveform developed, a single coil AC generator will be used. As the magnet in this generator is rotated counterclockwise, the magnetic north and south poles cut across the coil, inducing a voltage and causing current to flow in the coil. The voltage output is 0 when the coil is not being cut by any magnetic lines of flux. This is plotted as 0 voltage at the 0 degree point on the horizontal axis. When the magnet turns through 1/4 of a complete revolution, the north pole sweeps across the coil and the voltage increases from 0 to a maximum value, causing current to flow in one direction. As the magnet continues to turn and completes 1/2 of a revolution, the voltage decreases until it reaches 0 again and the current stops. The magnet continues to rotate, causing the south pole to sweep across the coil. The voltage now reverses polarity and increases to its maximum negative value, causing current to flow in the opposite direction. The voltage decreases again to zero when the magnet completes one rotation and the current again stops. The waveform shown is known as a sine wave. It's called a sine wave because the amount of voltage generated is proportional to the sine of the angle between the coil and the magnetic field. When the waveform of an AC voltage passes through a complete set of positive and negative values, it is called one cycle. It can be displayed on an instrument called an oscilloscope. The number of cycles generated in 1 second is called the frequency. The symbol for frequency is F and is expressed as frequency equals cycles per second, abbreviated as F equals CPS. In recent years, the term cycles per second has been changed to hertz in honor of Heinrich Hertz. This is abbreviated as Hz. Therefore, the frequency of our example is written F equals 4 hertz. A frequency of 25 cycles per second would be written 25 hertz. AC frequency is important to understand since most AC electrical equipment requires a specific frequency in addition to the correct voltage and current for proper operation. The standard commercial frequency used in the United States is 60 hertz. Now, let's analyze the waveform of an alternating current cycle. The time it takes to produce one cycle is called a period and is measured in seconds. The symbol for a period is capital T. You can observe a definite relationship between period and frequency. The higher the frequency, the shorter the period. If the frequency is 5 hertz, then it takes 1/5 of a second to complete one cycle. This relationship is shown as period equals 1 divided by the frequency. The equation is written T equals 1 over F.